Hello and welcome everyone to our webcast today on how to save money by reducing condemned pole replacements by up to 25%. My name is Mike McGill. I'm a Director of Sales for the utility industry here at Ike GPS, makers of GE MapSight. I'm joined today by Wayne Hall, Vice President of Reliable Lines. We're excited to be hosting Wayne today because it gives us the opportunity to showcase MapSight in the broader context of helping our customers manage the cost of their pole inventory. Before we get started, please note the following about today's webinar. We are recording this event and we'll be posting it online. We'll provide a link to the broadcast recording to all registered attendees via email. If you have a specific question, you can use the questions section located in the Ready Talk control panel on your screen. And we've set aside plenty of time today to answer questions at the end of the webinar. Please feel free to post your questions at any time during the presentation and we'll address them during the Q&A session. Since today's webinar is sponsored and hosted by Ike GPS, makers of GE MapSight, allow me to offer a quick introduction. MapSight is a software and hardware solution that enables pole owners to perform detailed pole inspections faster, safer, and with better results. At the core of the MapSight solution is the unique device you see on your screen right now. The MapSight device is unique because it's the only commercially available device that combines a laser rangefinder, sub-meter GPS, digital camera, best-in-class compass, inclinometer, and Windows mobile computer in a military-tough IP67 compliant ruggedized container. The result of combining all these elements into a single, simple-to-use device is that our customers are able to measure and locate poles faster and more accurately, while at the same time producing photo-verifiable and measurable evidence of what they've collected. Here's an example. Using the combination of MapSight's digital camera, laser rangefinder, compass, and inclinometer, we're able to produce calibrated images of utility poles and measure attachments on utility poles with an accuracy of 1 inch or better. And that's a result of combining all those capabilities into one device. Our capabilities and ease of use are just one reason why our host today, Wayne Hall, decided to use MapSight as part of his process for non-intrusive pole inspections. So with that, welcome Wayne to our offices here in Colorado. Welcome to the webinar and thank you for being here.
Thank you, Mike. Appreciate the introduction to the GE MapSight tool. And as Mike mentioned, it's one of the critical tools that we use in our pole inspection and reliability analysis process. What we're going to cover today, we're going to talk a little bit about some common pole management issues that our clients face regarding resourcing, regarding which poles to swap out and which poles can stay in for an extended period of time. We're going to talk a little bit about how we use different management tools to help solve those pole management issues. We're also going to look at the NDT, the non-destructive technology that we use in our processes with our clients. And among those key tools that are used during that process, of course, is the GE MapSight tool. We have a number of different NDT devices, non-destructive technology devices. We have a cloud-based data warehousing system, and we have tablet-based algorithms. So we'll walk through that tool set as part of the presentation. We'll talk about the assessment of results as well, and how to turn the pole inspection process from a yes-no type approach into an ongoing pole management system to allow a utility to actually start identifying deprecation rates within their individual networks. We'll also look at probability of failure analysis. Once we've reviewed and inspected a pole and we've determined that it should perhaps be swapped out, the next question is, when should it be swapped out? And so what we can do with our analysis tools is create a probability of failure analysis for an individual pole to enable a utility to use their resources most appropriately. Some of the common asset management issues that our utility clients face cover three key areas: utilization of resources. A very common issue among utilities is that there's quite a short time frame during summer whereby which they can use their linesmen to swap out poles. Also the reduction of waste. What tends to occur with a large number of utilities is a certain amount of the poles that they do pull as part of their pole replacement process tend to be in relatively good condition. Also the idea about improving the management of the process. So if we can help a utility determine the probability of failure for a pole and the expected time that they should swap that pole out, we can give them a best estimate for the most cost-appropriate replacement time for a pole. Another big issue that's faced by a number of utilities at the moment is the aging infrastructure base. The fact is that once a pole goes into the ground, it does get older, and a large amount of the pole population has been installed in the 1940s, 50s, and 60s. Now, given that the average pole age tends to be around about 35 to 55 years, what we're approaching in the next decade is an impending capex crunch, where more and more utilities will have to swap out a larger and larger number of poles. So as an attempt to help a utility manage the process, to identify which poles to swap out, to help manage their capital spend process, what we've done with Reliable Lines is created an integrated pole asset inspection process. Central to that process, we have a data mart. The data mart is a cloud-based data mart. It integrates to different GIS systems. It integrates to different third-party workflow systems. And it integrates to financial systems. As part of that cloud-based data mart process, we of course track the asset, we track the inspection event or the maintenance event, and we also track the service request related to that particular asset. In the field, we deliver an application via a tablet which allows the field-based inspectors to use algorithms that have been developed to estimate the percentage remaining strength of the pole while they're in the field. As part of that inspection process, we allow the use of NDT, non-destructive technologies, and we are somewhat agnostic about which NDT we use. We of course have some that we've calibrated extensively, but we are quite open to using multiple NDT solutions for this integrated solution set. We also can pull in manual measures, and as part of that process, we can also pull in and mass update GE MapSight IKE files. So by having an integrated solution that can be integrated into an enterprise architecture, what we allow a utility to do is deploy a very quick pole inspection process, which they can then integrate into their enterprise. And it allows them to do certain things, like manage several contractors on the same network. It allows them to run reports and accrual reports against the status of their inspections based on the scheduled timeline. What we'll do now is go down and look at some of the individual tools and how they're used in that process. And of course, the reason that we're here today is we advocate the GE MapSight product. The reason for that is it's the best product for measuring utility poles on the market. What it allows, of course, for those folks who do not know about GE MapSight, is it's a GPS, a laser rangefinder, a computer, a camera, a compass wrapped into one. So because it's aware of its situation and because it has a laser rangefinder, it can measure any other point that can be targeted with the laser. Now we find that particularly useful in several areas. The first area, of course, is measuring the height of the pole. What we have as part of our process is the requirement to get an accurate measurement from ground line to tip of pole. We also need to measure the circumference at ground line and at 6 feet. So those two measures are what we use in what we call a base inspection process. The operator enters in details about the pole into our tablet, and of course there is a number of standard fields within that tablet that get entered by the operator. There is, of course, a workflow, work packet numbers. There are details about the pole, the species, the class, as I mentioned, the height from ground line to top, the circumference at ground line at 6 feet, whether it's got deep cracks or checks, what sort of treatment, and of course we take pictures of the pole when we're on site. Once we've done that, we then extrapolate from the algorithms what's called a threshold value. A threshold value for us is the time of flight for a test, a sound test through the pole, which gives us an understanding of whether that pole or the inside of the pole is deprecated or not. So by having a threshold value and by using one of the non-destructive testing technologies against the pole, we can quickly tell if the pole has some sort of interior decay. We tend to use 3 non-destructive technologies with our client base, but as I mentioned, with our integrated solution, we are somewhat open to using other NDT and manual processes. I'll talk a little bit about the SB800 first. The SB800 is what's called an ultrasonic tomography device. What it allows an operator to do is actually record the time of flight of sound through the pole. Now, if the sound takes longer to go through the pole, it means the sound is going around some sort of decay or deprecation, and therefore it's an indicator that there is something wrong within the inside of the pole. We also have a pole radar unit. A pole radar unit is essentially putting a radar beam similar to a torch or a flashlight beam through a pole, and the reflection that comes back from decay is recorded in the algorithms we use to identify that decay. The difference between the 2 devices that we've just spoken about is that the radar unit is particularly useful in situations where you have concrete or asphalt around the pole, and you don't necessarily want to do a partial excavate to do some sort of subsurface or below ground line testing. We also have a pole tester under development. The pole tester is essentially an ultrasonic tomography device with 8 sensors on it to speed up the actual full test process. The output from a full test on the right hand side is essentially an MRI type view of the condition of that pole at that particular level. So most often our clients find that interior decay happens at or just below ground level, and so the SB800, when it's used at a ground level point, will actually indicate and show any deprecation of cells within that pole very quickly. Once the operator has tested and run a scan on the pole, the scan automatically also calculates out a percentage of remaining strength, and we then synchronize that data up into a cloud-based database. So from an asset management point of view, we can allow a utility to say, of the 3 or 5 or 30,000 poles that we've tested, we can stack rank them by percentage remaining strength, and we can focus our resources on swapping out the poles with the lowest percentage remaining strength. So that is one quite simple way that we help utilities manage and identify where to use their valuable resources and where to focus those resources to increase the reliability of their network overall. We then take the idea about whether a pole can remain on site or not to another level. Of course, percentage remaining strength is a very good indicator, and most utilities use that as their dominant requirement for swapping out a pole. But we then use the GE MapSight tool to take a range of other measures regarding the pole in order for us to do what's called a reliability assessment. A reliability assessment is the ability to look at the pole structure, to understand the environmental considerations around the pole, and then to develop a probability of failure analysis for that particular pole based on the unique characteristics of the pole. So a very common scenario, for instance, and most folks who work with networks will have seen poles which may have anything down to 8 or 9% original strength, and yet the pole will still be standing because the conductors are actually holding it up. And so it's quite common for those poles, especially if they've been reinforced appropriately, to stay or to be able to remain in service for a longer period of time. So one of the key measures, if we do a reliability, of course, therefore, is what sort of stress or support are the conductors, the strains, the cross arms, the attachments, any taps on the pole. What sort of support are they providing the structure, given that the actual percentage original strength is deprecated? So quite often, a utility that works with our reliability assessment tool will say, you know what, I know that the standard tends to be swapping out every pole with 70% or less, but because we are looking at this from a reliability point of view, we're going to do a reliability analysis on any pole between 50 and 70% original strength, because those are the poles that we can use as potential buffer to push them out into future seasons or years of work. If we can do a reliability analysis on those marginal or just failed poles, then we can actually identify which ones could perhaps remain on site. A very common use of this sort of idea is if that particular part of the network is going to be upgraded anyway in another 3 to 5 years. So instead of spending the capital to replace the pole, a utility will run a reliability against the poles that have failed and determine whether the likelihood of them of failing is so small that it's worth leaving them in there until the upgrade is complete. On this view here, therefore, you can see if folks are familiar with one of the outputs of GE MapSight, and that's a KML type file which can be viewed through Google Earth, and it shows a very good schematic of where the operator for this particular reliability assessment was positioned when they took different missing line measurements and different true size pole measurements in order to provide the depth of information that we need to do an appropriate reliability analysis on a pole. Of course, understanding the span length or distance between poles, understanding any taps from those poles, and using true size pole to measure the height of conductors, the height of cross arms is necessary for the reliability approach. So it becomes very obvious when an organization decides to look at using reliability that it is essential to use a measurement tool that can not just measure and track the GPS locations of different points, but also provides a reliable and auditable system behind it. So the outputs from the GE MapSight measurements for reliability, of course, include photo verification of those measurements, so that when the engineers are reviewing the reliability assessment to determine whether, yes, they will accept that report and leave the pole in service for a number of years, they actually have an auditable set of information to review as they're making that decision. So the next slide shows another, on the left-hand side, another tablet screenshot, which shows some of the elements that we look at as part of that reliability assessment. What we'll do is we'll actually take wind profiles for a particular area over a return period of up to 50 years. We'll look at the soil type. We'll look at the type of climate, the ice thickness on the pole, and then what we'll do is we'll develop a bell curve of the expected force that will be applied against the pole, and that bell curve is highlighted in blue. After we've measured the pole with the GE MapSight system, and after we've entered in details about the conductor angles, the span lengths, the angles of any supports, any trusses that are on the pole, then the algorithms within the tablet will calculate out an expected value or the ability of that pole or structure to withstand force. And so that's what the green bell curve is. The ability of that structure to withstand the force that's applied against it, based on a return period of 50-year extreme wind gusts. By definition, therefore, the intersection of those two bell curves is where the probability of failure for that structure is. You have the expected force, you have the expected ability of the structure to withstand the force, and therefore you can calculate out a percentage or a probability of failure percentage. We then turn that into what we call a reliability index. So a reliability index for this particular pole is just under 2, 1 being hazardous or very poor, and 6 being good. So for this pole here, it's got quite a high probability of failure, and therefore it's assessed as poor. We can also extrapolate out what's called a TTF, a time to fail in years, 2.5 years. So our assessment of this pole after we've done a reliability analysis on it is it's pretty marginal, and it's probably something that should be prioritized for replacement within the next year and a half in order to give the utility a little bit of a buffer on the reliability assessment within the system. So what is the payback from this type of approach to managing a pole population? Well, the first one is it's a non-destructive process. So it complements a standard inspection process quite well because it provides the ability for a utility to reassess the red tag poles that may have come out of their regular inspection program. But of course, when we're doing that retest, we don't necessarily want to put more holes in the pole itself. The second payback is it's very consistent. Because we're using accurate measurement tools, because we're using reliability algorithms, because we're using a non-destructive test device that has an electronic read, we can provide a very consistent analysis of those poles and a very granular analysis as well. So if a utility has a scenario where they have 500 red tag poles in the field, they can retest them and run reliability on those 500 poles. And if they only have resources to swap out 200 for that particular season or year, then they can of course apply their resources against the most hazardous poles first. It also provides a management platform. Because we are now tracking the pole inspection at a granular level with a large number of outputs and parameters regarding that pole, we can start tracking and recording a history for different poles that we may decide to leave in the network. And part of the payback of that is an individual utility network then starts creating their own corporate knowledge about the deprecation rates that are particular and unique to their network. Because of course every network has different influences from both a climate and an age profile point of view. We regularly get customers reporting to us that 25% of their condemned poles can be actively managed to subsequent periods using this type of approach. We have actually had some utilities get far higher results than that. So the essence of the return on investment for this type of process is the minimal investment of several $100s to run a reliability assessment compared to the swap out cost for a transmission pole or a distribution pole with a lot of attachments tends to be quite high. So the ability for us to provide a granular view and allow the utility to focus those resources is particularly compelling for utilities. We'll just go back briefly to the SB800, the ultrasonic tomography test, just to provide a little bit more of a layer of information about how that test looks with regard to live poles. So for instance, we have a transmitter pole probe and we have a receiver probe. And the way that ultrasonic tomography is used to test a utility pole is that we will put nails in 8 points of the pole at the level that we want to test the pole at. So if we're testing for ground line internal decay, of course it will be ground line. We have a number of clients that use this technique to measure and estimate the extent of pocket decay in transmission poles. So of course pocket decay can happen anywhere in the pole. The basic process, however, is by having a transmitter probe and a receiver probe and timing the flight between those probes is when the sound intersects with some sort of internal decay, the actual sound travels around that decay, and therefore it takes longer in microseconds to get through to the receiver probe. So by taking a number of measures, we're actually taking a number of vector points throughout the pole, and from that we are creating an image of what the decay area within that pole looks like. So the decay in the pole is measured in red, Goodwood is green, and you'll notice that there is actually some red outline, and this indicates that the inspector has identified some shell rot. And on this particular pole it looks like he's probably entered in 1/4 inch of shell rot. So the shell rot assessment using this process is used using a mold probe approach or as part of the partial excavate. The report from that full scan then gives that percentage of original strength for that particular pole. We have here a couple of examples of poles that have been tested in the field and the resultant tomography view on the side, and you'll notice that this pole on the right hand side, there is deprecation in this area here, and in fact as part of that deprecated part of the wood, a woodpecker has actually drilled its way into the side of the pole and created a woodpecker nest. This image here is a large transmission pole, and the internal of the pole has been completely rotted away. So when we look at this internal here, it was essentially a mud type mix. The outside of the pole was still very healthy, and it actually passed its acoustic or hammer test. But using ultrasonic tomography, we could identify that the entire internal of it was decayed on the left hand side. So what we've covered today, we've talked a little bit about common pole management issues. We've talked about using a non-destructive technology to perhaps run a retest or reassessment of some of those red tag poles, maybe to use as a complementary test to the standard test that's being run by a utility. We've looked at some of the key tools used during the process. Of course, the GE MapSight tool is critical for us in order to create an accurate and granular assessment of the quality of the pole using the probability of failure approach. We've talked about the assessment of some of the results and how we can use a simplistic stack ranking of percentage original strength to allow a utility to focus their resources on the most hazardous poles first. And of course we've talked about that probability of failure analysis process.
Wayne, thank you very much. Appreciate that presentation. I've got a couple of questions for you. First, just simple technical question. What type of device does your application in the field run on?
A Samsung tablet, an Android device.
So basically any Android device?
Typically we recommend a 7-inch or the 10-inch, just from the point of view of the form factor. We recommend a 10-inch.
Okay, and how do you take information, data from the MapSight device and get it into your application?
So we have a bulk load process that runs on the cloud side. A administrator at the utility, after the staff have brought the MapSight device back into the office, they will synchronize those files to the GE MapSight software on a desktop, and the operator will open up a browser to our cloud and point to the location of the files, and it may be several hundred files if they've been out for a week or more. And as part of the upload process into the cloud, we have a secondary process where we open up the IKE file within that MapSight software, and we process that information into our database automatically. Of course, the key benefit to that is there's no transposition issues regarding manually cutting and pasting measurements from one device or one set of information to the other.
And then I'll selfishly underscore that you end up not only are there no transposition errors, but you end up with photo verifiable evidence of the information you've collected in the field, which I think is helpful.
That's exactly right. Part of that read of the IKE file, of course, identifies where the IKE image is, and we upload that IKE image as well, and that's attached to the record. So it goes back to that idea about having an auditable, traceable process. If an organization is making a decision about a utility pole, especially where it's a critical pole, then the engineers need to be able to look back at the measurements from the field staff themselves.
And then that information is readily available in customers' GIS?
So what we do is we can push that information back into a customer's GIS system through a back-end integration process, or our partner Empower Innovations actually have an integration layer that they've developed with us that allows us to populate that information back into a GIS system.
Very nice. Can you provide us with some examples, Wayne? The traditional method of doing these pole inspections is intrusive and potentially causes more damage to the pole, but it's something that utility companies have been doing for years. Can you provide us with some examples of how your customers are able to get comfortable with leaving the old method behind and moving to this new non-destructive methodology?
Yeah, so there are, I guess, 2 points to that. One is perhaps the customer won't move off their current process. Perhaps because their standards are that they bore and measure a standard bore, that they'll remain with that. But what we do is we complement it with regard to red tag poles that they have. As part of that standard process, of course, they will have failed poles. We can then use our process to test those red tag poles. We can run a reliability assessment against them in order to give the utility a second layer of assessment only against the red tag poles. So that's the first point. We see ourselves as quite complementary to a standard bore, visual, acoustic, and excavate process. The second point is we do have some utilities that decide to just use an NDT approach. Before they take that, they invariably will continue their manual process and they'll run a pilot with us of several hundred poles, and as they pull the condemned poles, they will actually look at the saw cut views where we've done that ultrasonic tomography to validate and verify that they're getting the correct reads.
So that's interesting. So this doesn't have to be an all or nothing proposition.
No, absolutely not. We see it as quite a complementary process to the standard inspection process. Because in some areas it's required that they do that, use that approach, and there's a large number of engineering standards within a utility to do that as well.
Okay. Well, it looks like those are all the questions that we have today. I would like to again express my appreciation to Wayne for being here today and providing this presentation. I think it's very helpful, and I found it very interesting. Thank you, Wayne. Thank you, everyone online, for attending today. We appreciate you being here. We know your time is valuable. Hopefully we use that time very well this morning or this afternoon. So with that, thank you very much. I hope you all have a great day, and we look forward to talking to you about solutions from reliable lines and from IKE GPS. Have a great day.
Thank you very much.